Mr. Queliotto here, and today we're going to focus on some different properties of isosceles and equilateral triangles. This triangle that we have pictured is an isosceles triangle. We know that because two of its sides are congruent, and here those sides are called the legs. The not congruent side is then called the base of this triangle. We label the angles that are next to these base side as the base angles. Lastly, we have the vertex angle, and this is just the angle that is formed by the two legs of an isosceles triangle. I'm going to refer back to these concepts, so you may want to write these down and maybe pause the video for a minute and just make sure that you are aware of these terms. This section has a couple of important theorems, and the first one is the base angles theorem, which basically just tells us that if two sides of the triangle are congruent, so we have here that AB is congruent to AC, then we can say that the angles opposite them are congruent, meaning angle C is congruent to angle B. So when we talk about the angle opposite of AB, we mean opposite angle C right here. And opposite AC, of course, would then be angle B. The converse of the base angles theorem is just, well, the reverse of it. We're just going the other direction. So before we needed two sides to be congruent, which would tell us the angles are congruent. In this one, if we have that angle B is congruent to angle C, then we can say the opposite sides are congruent. So opposite side to angle B, of course, is angle AC. Side AC is congruent to, opposite of angle C is side AB. Let's put these theorems to use. Here we're given that JK, side JK, is congruent to JL. So we'll go ahead and write that up here. JK and JL. And JM bisects KL. From prior knowledge, if we know that it bisects, that means it does split it in half, so we can assume that these are going to be congruent. But again, that's part of the proof, so we need to write that down as reasoning. So I'm going to start off by just writing our givens down. And I already have the statement column filled out pretty much. Step 1, that was given. We also have that JM bisects KL, so again, that's given. I'm just going to write the two tick marks to indicate I'm writing the same thing. Now, Km is congruent to Lm by the definition of angle bisectors, or excuse me, the definition of a segment bisector. It bisects segment KL. In step 4, Jm is congruent to Jm because everything's congruent to itself by a property called the reflexive property. So next step in the proof, it says triangle JML is congruent to triangle. Well, we have to ask ourselves now, why can we say these are congruent? Well, we've already decided that we have three congruent sides, so we can say that these triangles are congruent by side, side, side. And just to name this triangle, make sure the vertices line up. So JML needs to line up with JMK. JMK. Lastly, we're trying to prove that these two angles are congruent. So if we have congruent triangles, to say that these two angles are congruent, we have to use CPCTC. Congruent parts of congruent triangles are congruent. And that's it. In these next two examples, I'm going to apply the theorems that we've already learned. So here we have two congruent angles, and using the converse of the base angles theorem, so I'll just write converse of BAT, base angles theorem. If we have that angle X is congruent to angle Z, we can say that 15 is equal to 4x plus 3. Solving for x, of course, we have to subtract 3 from both sides. We get 12 is equal to 4x. Divide by 4 to clear that coefficient. And x is equal to 3. piece of cake once you know the theorem. Second example, we have two given sides and we have to find the other angles. Before we continue with the second example, I do want to apologize. This is supposed to say 11x minus 18, and we'll continue from there. Now, this example has us using a couple different things, because if we notice that we do have two congruent sides, so using the base angles theorem, what we can say is that angle F is congruent to angle D, meaning they're the same measures, but we don't really have measures for those. We know that the insides of a triangle, though, add up to 180. So 180 is going to be 40 plus 11x minus 18 plus another 11x minus 18. We can add 11x minus 18 twice because we know that, using the base angles theorem, this should also be 11x minus 18. So we just have to carry out the algebra, combining like terms. Remember, here's the equality sign. So you can only add or subtract to one side. Whatever you do to one, you have to do to the other. So I'm first going to add up like terms on this side. We have 40 minus 18 minus 18. That leaves us with 4. And 11x plus 11x is 22x. So we're left with 180 is equal to 4 plus 22x. Subtract 4 from both sides, and we have 176 is equal to 22x. Then dividing both sides by 22, we end up with x is equal to 8. And we're done. Now if the question asked us to solve for the measures of each angle, you would plug 8 back in for x. But here, finding x is all I'm looking for, so we're done. There's two more things to look at here, and it's the corollary to the base angles theorem and the corollary to the converse of the base angles theorem. Basically what a corollary is just an extension for a specific case, and our specific case this time is the equilateral triangle, which is also an equiangular triangle. If a triangle is equilateral, so all the sides are the same length, then we can say that it is equiangular. So if all of the sides, as written here, are congruent, we can say that all of the angles are congruent too. Angle A is congruent to angle B is congruent to angle C. The corollary then is just the reverse, where we take all of the angles are the same and we go the opposite direction. In this last example, we're going to solve for both x and y. To start this, we can use the base angles theorem. We have two sides that are congruent, so we can say that these two angles are also congruent, and those are the angles opposite of these congruent sides. So the angle opposite of this side here is 10y minus 41, and the angle of this side here is 6y minus 5. Let's set those equal to one another. 6y minus 5 is equal to 10y minus 41. Now we just have to combine like terms and solve. So we add 41 to both sides to cancel out the 41, and we subtract 6y from both sides to cancel out the 6y. We're left with 41 minus 5, which is 36, is equal to 10y minus 6y is 4y. Last, we divide both sides by the coefficient in front of y. 36 divided by 4 is 9, so y is equal to 9. The best approach to solve for the value of x is actually to plug in the value for y to solve for these two congruent angles, and then go from there using the fact that all of the angles of a triangle add up to 180 degrees. So we'll start by plugging in y. 6 times 9 minus 5 is equal to that angle. So 6 times 9 is 54, and minus 5 is 49 degrees. So each of these angles now are 49 degrees, 49 and 49. Which means that this third angle would have to be 180 minus 49 minus 49. So that's 180 minus 98 is equal to 82 degrees. Now we have that 82 degrees is the measure of this angle. So we can set 82 equal to 12x plus 22 to solve for x. Subtract 22 from both sides, and we're left with 60 is equal to 12x. Divide both sides by 12, and x is equal to 5.